Well, greetings, mathletes, and welcome back. So last time we took a look at what to do with the end game, right? How to solve a trig equation when you have a trig function equal to a value, and then how to represent all those answers. What we're going to look at today is everything up to that, because every trig equation ends that way, but they don't all look that way to start with. And so your goal today is to try to get those trig equations to look like the ones that we did last time. So let's go ahead and take a look here and see what we got. Um, let's see. So let's take a look at our first example. Let's see, I have that on. Okay, so let's get rid of that. Back here. Okay, so our first example is this one. So we got 2 sine squared x minus sine x minus 1 equals 0. Okay, so looking at this, it may or may not jump out to you, but this is actually a quadratic equation. But instead of a quadratic equation in x, it's a quadratic equation in sine squared. So first I want to remind you that whenever you see sine squared x, this is the same thing as sine x squared. It's just a shorthand. We've been using it up to this time, but I really wanted to remind you because it does make a difference right now. So these right here, when you have a sine squared and then a sine and then a constant or whatever, you notice that this really is a quadratic. And so that means you're going to need to factor it. I think it's a little easier to factor it if you make a substitution. So if I just go ahead and decide that u is equal to sine x, right? Then that means that u squared is equal to sine squared x. And that's both of our substitutions there. So I can take out the sine squared x and I can put a u squared in its place, and I can take out sine x and put u in its place. So I end up with 2u squared minus u minus 1 equals 0. And we're just going to deal with this in terms of u. We're going to forget that we have trig equations for the moment. So we need to factor this thing. So let's see here. That leading coefficient is not a 1, so I'm going to have to use the master product and grouping. So that my master product is 2 times negative 1. The sum I want is negative 1. So my magic numbers are going to be negative 2 and 1. Because they multiply together to give me negative 2 and they add together to give me negative 1. And so I'm going to use that to separate the middle term. So it ends up being 2u squared minus 2u plus u minus 1 equals 0, right? And then we split between the front end and the back end. And it looks like 2u is our common factor up front, and that leaves me with a u minus 1. And then back here, our common factor is just 1. So I'm going to pull out a 1 and leave a u minus 1 here. You don't have to pull out the 1, but it really makes it a lot easier to see what the factor is if you do. So now I have one factor that's u minus 1. So I'm pulling that out now. And you notice if I pull out the u minus 1, it leaves 2u plus 1. Okay, now if you remember solving quadratics, once you have it factored, you set each factor equal to 0, right? So, in fact, I'm going to need space over here, so I'm going to carve it out now. So that gives me u minus 1 is equal to 0, or 2u plus 1 equals 0. So this one gives me that u equals 1, and this one, it gives me u is equal to negative 1/2. Okay, so those two solutions, but they are not solutions to the trig equation. They are solutions to this quadratic. We need to remember that u is equal to sine x. So this is actually the equation sine x equals 1. And this one is the equation sine x is equal to negative 1/2. Okay, so really we just need to find the values of x that will give us those two things when we take the sine of those. So I like to look back at the unit circle when I think about this. I'm not going to put in exact values particularly. I'm not drawing the whole thing. I'm just getting an idea of what's going on here. So here, sine x is equal, I'm going to write that first. Sine x equals 1. Okay, remember sine is your, what do you call it? It's your y value on the unit circle. So the only place sine is equal to 1 is right here, right? It's that vertical distance from here to here. So the only angle that's going to give me sine is equal to 1 is pi over 2. So that means here, x is equal to pi over 2. That's one answer. Now, the other thing is we have is sine x is equal to negative 1/2. Okay, so that's actually down here, right? And that happens at negative pi over 6. If we convert that to a positive, basically, if this side is negative pi over 6, we just need to add 2 pi, and that will give us, in fact, let me write this out so we can see it first. Oh, I thought I switched that. So sine x is equal to negative 1/2, right? So it's equal to negative 1/2 right here. And that angle right there, since it's pi over 6 down, what that means, since the whole circle is 2 pi, that means I have one solution here at 11 pi over 6, because 12 pi over 6 would be 2 pi, right? So it's pi over 6 shy of that. So that's one, but remember the sine is actually this vertical height, and I have another place over here that I have the same vertical height. And this angle down here is going to be the same as this one. Let me switch that color so you can see it better, right? So if I draw this angle here and this one here, this vertical distance and this vertical distance are going to be the same distance, right? And they're both negative 1/2. So we just need to figure out what angles they are. This angle with the x-axis is going to be the same on both sides. And since this is pi, right, and that's pi over there, that means it's pi over 6 past that. So that makes it 7 pi over 6. So that means my second solution is 7 pi over 6. And you notice I did that using the picture, right? The picture really does help. You have to be able to visualize it. Most of the time when I'm coming up with trig values off the top of my head, I'm picturing the trig, the unit circle, right? I'm looking at those side lengths and all of that stuff. So now what this just did, since we were looking at one revolution of the unit circle and we found all the solutions in there, we have one here, and one vertically right there. And that's everything in one revolution. So these are all of the solutions on the interval from 0 to 2 pi, right? And that's typically what you're going to be asked for on these, because you can always just add 2 pi to all of the solutions to get the next round of solutions. Okay, so that's our first example. So I want to point out that the last part of this was pretty much the same as what we did in the last lecture. What was different is that we had to treat this like a quadratic first and use some other techniques from algebra. And that's typically what we're going to see today. There are some places where we're going to have to make some trig substitutions, right, to make sure we do things okay. But I think it's gonna work out pretty well. Okay, so let's go ahead and clear that out, and we'll look at the next example here. Okay, so next example, and I actually want you guys to work on this one. I want you to try this out, see if you can get through it. 2 cosine squared x plus 3 cosine x plus 1 equals 0. So see what you can do with that. Go ahead and pause the video here and see if you can walk through it. I'll give you this much of a heads up. There are 3 solutions, and actually I should say this. Find solutions for x on the interval from 0 to 2 pi. You don't have to find the infinite number of solutions. And I'll tell you this much. There are 3, right? There's 3 on the interval from 0 to 2 pi. So see what you can do with it. Go ahead and pause it here and go. Okay. Now, I do want to say that if you can see how to factor it without using the substitution of u, you're more than welcome to do that. A lot of people do that, and once you get a little more comfortable with it, you'll see it just starts to happen. But until you're there, the substitution in this case is going to be to say that u is equal to cosine x. Okay, so that's going to transform our entire equation into 2u squared plus 3u plus 1 equals 0. And we can factor this out. Let's see, how is this going to factor here? Yeah, I'll go through the whole process. I was debating on whether I just wanted to write down the factorization or work it out. So it should be 2 and 1 there. So that means I'm breaking it down to 2u squared plus 2u plus u plus 1. Right? And we'll split here. And that means 2u is my common factor. So that gives me a u plus 1 here. And the back side, I have 1 as a common factor. So that also leaves me with a u plus 1. So I end up with 2u plus 1 times u plus 1 equals 0, which means 2u plus 1 equals 0, or u plus 1 equals 0, which again gives me that u is equal to negative 1/2, and u is equal to negative 1. Okay, but we have to remember that u is actually cosine x. So this is actually, in fact, I'm going to jump up here now, and let's just switch. So, because we're working on a different part of the problem here. So now it's cosine x is equal to negative 1/2. So we have to find all the solutions to that. And cosine x is equal to negative 1. So again, unit circle. Remember, cosine is your x value on the unit circle, right? And remember that that's pi, that's 3 pi over 2, and up here's 2 pi. Nonetheless, looking at this, where cosine is equal to negative 1/2, remember it's the x value, so that means that cosine is going to come out here to about 1/2, not about, exactly 1/2, and we're trying to figure out what this angle is here. Okay, keep in mind that cosine is also 1/2 down here. This is clearly not a very good drawing, but those are two different angles that we have to find. So, looking at this, you should be able to get the first one here is 2 pi over 3. And that means that you have pi over 3 on this side and pi over 3 on this side, right, for the angle. These two angles are the same. So this means that it's pi over 3 past pi, which makes it 4 pi over 3. So now we have two values here. X is equal to 2 pi over 3 and 4 pi over 3. Now, where cosine is negative 1, remember it's your x value. I'm going to redraw a little unit circle here. Right? If cosine is negative 1, the only place that happens is right there. And so it's this angle here, which is from here around to there is pi. So that means that x is equal to pi. So we have three answers on the interval from 0 to 2 pi. We have x equals, well, typically they're written in order from smallest to biggest, but that's not the law. I'm just going to do that, though. 2 pi over 3 pi and 4 pi over 3. Right, so those are the three answers you should have got. All right, so let's go ahead and take a look at our next one now. And we're going to twist it a little bit. Of course, we always do. Yeah, so let's go ahead and, wait, that didn't delete. Let's try it again. Delete. Hey, there it goes, I win. Okay, so let's look at the next example. Now, many of these take a little work before you can get them to a point where you can actually factor them or do anything else with them. So we're going to add that layer of complexity in here. This one actually requires a trig identity to be able to substitute in to turn it into something you know what to do with. So what I'm interested in is seeing if you can find what that substitution is, that trig identity is, and see if you can get this into a form that you know what to do with, right? So let's go ahead and start there. Go ahead and pause it and see if you can walk through it on your own. If you can't see it, that's fine. We're going to walk through it together. And this one is, it might be something a little outside of what is obvious to you, but at the same time, it is certainly something that's known to you. So see what you can get. Go ahead and pause it here. Okay, so assuming you've already worked on this, hopefully what you realize is that if you take the Pythagorean identity, cosine squared x plus sine squared x equals 1, if you subtract sine squared over, I get that cosine squared is equal to 1 minus sine squared. Okay, so this is valuable to me because that means I can substitute that value for cosine, that value for cosine, turn it into a sine, and then I have an equation with all signs in it. And that I can probably do something with. So let's see what we can get here. So cosine squared is 1 minus sine squared. So that turns us into this. 2 times 1 minus sine squared x plus sine squared, or plus sine x minus 1 equals 0. Okay, so now let's go ahead and distribute this 2. So we end up with 2 minus 2 sine squared x plus sine x minus 1 equals 0. And if I just go ahead and collect my like terms, it looks like the only one I really have is the 2 and the negative 1. I end up with negative 2 sine squared x plus sine x, and then that would make it a plus 1. 2 minus 1 is 1. Okay, equals 0. Now, I have it into that quadratic form, which is actually really nice, but I have a problem with the fact that my leading coefficient is negative, and that's not a typical way we look at it. So what I can do is just multiply the entire thing by negative 1 and switch all of the signs at the same time. Because I'm multiplying both sides of the equation by the same number, it doesn't change anything. So this now becomes 2 sine squared x minus sine x minus 1 equals 0. Now, this is actually quite fortunate because this was our first example today. Right, that's the form that you got it in. Now, you notice we had to massage it a little bit to get to that form, but that means now we have the same solutions as we had before. So I'm actually just going to go ahead and write it down without doing the substitution of u, just so you can see what it looks like. So when I factor these, what I end up doing, I see that I have a 2 sine squared. Now, the only way I could have a 2 sine squared is if I have 2 sine x times sine x. That's the first thing that happens when I FOIL, right? When I distribute. Okay, now the middle term, which is negative 1 here, needs to be this, this times this plus this times this. So it's your inside and your outside terms. And I need one of those to be a negative 2 and one of them to be a negative 1 so that it adds up to negative 1. So if I'm going to get a negative 2, this has to be a negative 1, and that makes this a plus 1. Now, you can always go through it and do it the way we did it before with the u substitution and using the master product and all that, but you'll get the same answer. We've already done this problem, so I don't mind skipping all the in-between steps on this. So yeah, I have two things here, and they're both factors, so I'm going to set each one of them equal to 0. If I have 2 sine x plus 1 equals 0, that's going to give me sine x is negative 1/2. The other one here, sine x equals 0. Oh, excuse me, sine x minus 1 equals 0. Gives me that sine x is equal to 1. Now you notice these are the same steps we had in the first problem, right? That's something familiar, and that was what we did after we substituted sine back in for u. Okay, so each of these gave us two solutions. We ended up with, for sine x equals negative 1/2, we had 7 pi over 6 and 11 pi over 6. And then for sine equals 1, we had pi over 2. Right? And so those are the same answers we got in that first problem. And that's because this was the first example in disguise. Right? So you may have to do some massaging with these to get them into a form that you know what to do with. And don't be afraid to use any of the identities that we've used so far. I think probably the most useful one is going to be this Pythagorean identity. So you can substitute out for sines and cosines squared. Okay, so I do want to look at one more example here. And we're actually going to look at one that mixes a tangent in there also, and some of the things you can do with that. Okay, so our last example here, let's take a look. We got, oh yeah, that whole turning on the pen again. Yeah, here we go. Okay, so we got tangent squared x times cosine x is equal to tangent squared x. And again, we're looking for solutions on the interval 0 to 2 pi, right? So you might have to do some sketches to make sure that you get it all. But see what you can do with this. There's a few different directions you can go on this one, and there's one that's probably the least amount of work, but there's more than one way to get to the answer with this. So see what you can do. No correct solution is incorrect, and there's plenty of correct solutions, although that was kind of a weird statement. No correct solution is incorrect. Well, it's true. Okay. Anyway, see what you can do with it. Okay, I'm assuming you've paused it at this point, and I'm going to take you through the most efficient solution, at least the most efficient one I see. There might be one out there that's even more efficient. I have no idea. There's a lot of ways to do these things. So if we go ahead and start off, what I know is that if I'm going to factor this, it has to be set equal to 0. So that's where I'm going to start. I'm going to take this and subtract tangent squared from both sides. Now, this one's a tangent squared times cosine, so they're not like terms. So what that leaves me with is tangent squared x cosine x minus tangent squared x is equal to 0. Okay, now what you would hopefully notice here is that tangent squared x is a common factor between the first and the second term. So that means that we can pull out tangent squared x. And this is where things start not looking familiar. Oops, not see. Cosine x minus 1 equals 0. Okay, but this is, these are two factors multiplied together to give you 0, which means that tangent x is a factor, or cosine x minus 1 is a factor, or tangent squared x, I mean. So that means that either tangent squared x equals 0 or cosine x minus 1 equals 0. Well, this one's only going to happen if cosine x is equal to 1, right? So we can work from there. Tangent squared x equals 0. Well, if I take the square root of both sides, that means that it's where tangent x is 0, right? So we can find solutions for both of these. Now, tangent, in fact, maybe I want to do it over on the side. Yeah, let me do it over on the side. Okay, so if I'm going to draw a tangent here, right? I know at 0, tangent is 0, right? And then I have, comes over here to pi over 2, right? But at 3 pi over 2, it does the same thing. And I have another one, another 0 over here, right? And then the next one happens at 2 pi because tangent repeats itself. Now, we were told to find things on this interval. Okay, so tangent x equals 0 when x equals 0, right? That's this one. Pi over 2 ends here. And the 0 and the pi over 2 is not included. This is a round bracket. So that means this is my other one, right? Halfway between pi over 2 and 3 pi over 2 is pi. So when x is 0 or when x is pi, tangent is 0. Those are the two times it happens. Now, cosine, well, if you want, I've been using the unit circle, but you can look at it this way also, right? Cosine x does this from 0 to 2 pi, right? Where is it equal to 1? And there's only one spot. It's right there, right? And that is when x is 0. And that is already covered over here. So we have all of our solutions now, right? I get I have x is equal to 0 and x is equal to pi, and 0 actually makes cosine 0 also, so we're fine. Or excuse me, 0 doesn't make cosine 0. 0 makes cosine 1. I knew something didn't sound right about that. Sorry. Yeah. So in any case, that's all of our solutions there. And you notice I didn't have to make any substitutions this time. I just had to be able to separate the equation out into two equations, and each equation had its own trig function, right? So as long as these equations, right, only have one trig function in them, you're fine. So if you can separate the factors out into separate trig equations also, that's a really good way to solve these as well. So one way or another, you need to get it down to equations that have only one trig function in them. But there are definitely different ways to do this. Okay, so I'm hoping that those examples will help you out. And until next time, keep your pencils and your wits sharp.